Hello and welcome. This is going to be your video instruction for the Gas Production Lab here for Chemistry 151 at the University of Indianapolis. I'm Brad Neal. I'm here to help you collect some data. Collect some data, you say? Yeah, because see, while you physically aren't here in the lab space to do this, and I am, you will be able to play along at home because we're going to show you all the information that you need in order to do this lab. This is a little technique. It's almost called dry labbing in the biz. You don't have to worry about that part. The part you do need to worry about is part one of this lab. So part one of this lab is we are going to try to figure out the volume of this really clear object that's hard to see, which is called an Erlenmeyer flask. We need to know exactly how much volume this thing has in it. And you're like, oh, it's got 125 milliliters in it. Not really, because that's where the line is. We need to figure out exactly how much volume is in it. But to make things more complicated, we need to figure out how much volume is in it when we put a stopper on there, because it's going to be different when it has a stopper on there versus when it doesn't, because see, like the stopper comes down and kicks out some of the volume. It's really fun. So in order to figure that out, we're going to do a mass displacement kind of deal like we did in Unit 1 when you were figuring out the density of a strange object, or you're going to be measuring the difference in volumes of things. So just keep following along. It's going to make sense. To figure this out, we're going to figure out how much fluid can actually fit in this thing by mass when it's got the stopper on it. So to figure that out, we need to use a balance. So to use said balance, always remember, start out with the thing being tared. You want it to be at 0. That'd be really good. In case you don't remember, hit the tare button, and hey, look, it's at 0, and it's got the little star, so it means you're ready and good to go. So now we can figure out the mass of our beaker and the mass of our stopper by themselves. No fluid in there. So we just put it on there, and Yahtzee. We got ourselves now the mass of the stopper and of the beaker. Great. How does this help us? Well, now we can take our beaker and we can take some water, because water is safe, and we're going to pour the water all over the beaker, and that's not really what we want to do. Good thing we got paper towels. We're going to put said stopper approximately the same height as it was before. Just getting rid of some of the excess water there. All right, and then we're going to dry off said glassware. Because if we do this now, and we come in, and we get a new mass, this is going to be the mass of the beaker, the stopper, and the water. So if we subtract out the mass that we took originally, that was just the beaker and the stopper, then we're good. I keep calling it a beaker. It's an Erlenmeyer flask. Why has nobody stopped me yet? Come on, this is how this kind of instruction is supposed to go. So you can figure out how much water is in the Erlenmeyer flask now by taking the difference of those. Why does that help you? Well, if you have the mass of water and if you know the density of water, you can figure out the volume of water that's in there, and that's going to be the volume of the flask. Now, at least one of you should be saying right now, isn't density temperature dependent? And doesn't density change based on temperature? And I say to you, good job. The rest of you, good job. Because you were thinking it too, you just didn't want to raise your hands. So we can go to a table that's going to say for the mass that you have measured at a given temperature, this is what your volume would be. So we need temperature so that you can go to the table, you can figure out the right density so you can figure out the exact volume. And here we got ourselves a nice little temperature of the room using the Logger Pro software and the Vernier probes and all that jazz. So if you now calculate the mass of your water, you look in the table, you figure out said density at the correct temperature, you can figure out your volume inside the flask. Congratulations, you did part 1. All right. Hopefully you watched the part 1. Hopefully part 1 made sense because we need specifically that volume from it. Now here we go into part 2. Part 2 is where we are going to actually do the reaction. And so this is according to your balanced equation, a reaction between hydrochloric acid and magnesium to liberate hydrogen gas. We're going to be using a setup demonstrated kind of by this to measure the amount of gas that comes off by measuring the pressure changes that occur as part of this reaction. So, remember the flask from part 1? That's right there. Remember the stopper from part 1? That's right there too. Now we have some more additions. We have a 3-way valve. So right now, open, closed, open, closed. Very exciting. And note how it has this nice little adapter right there. We're going to be able to have this here syringe that we're going to use in a little bit, and it's going to connect nicely to that there adapter. Okie doke. The other thing that's in our stopper is this nice little hose. This nice little hose is connected to this nice little gas pressure sensor, very aptly named. The gas pressure sensor senses gas pressure changes, kind of in the name. It is connected to box is connected to computer. Computer gives us output of temperature measured via a temperature probe that's sticking in the water bath, and pressure. Please note the units on both of these. This is going to be important for your calculations. Okay, make sure you watch those units. So, before we do the actual reaction, we need to make sure that this setup is not leaking gas. And the way that the reason that's so important is because we're producing hydrogen gas, and in order for us to figure out how much hydrogen gas is produced, we can't have any of it escaping. If it escapes, our pressure is wrong, so all of our calculations are wrong. So here's our quick and dirty pressure testing for our setup. We're going to take our syringe and we're going to pull an indiscriminate amount of air in it. I put 20 milliliters because 20 milliliters seems like a nice number. If it was a 21, maybe I would do that. I don't really know. I just pulled it to 20. It's very exciting. We're going to now connect it, and we have to be careful. It's a screw connection here, but we don't want to screw it on so tight that it strips. Okay. We have this in the closed position. Very exciting. We're now going to do the test run using the software. So the Logger Pro software is all very nice, and this is not a touch screen, so we're going to have to use this antiquated thing called a mouse to click connect. So we hit our collect. Yeah, there's an L there, it's not an N. Collect. Okay, Yahtzee, it is now collecting data. It is measuring the temperature of the water. Now in this reaction, when we actually do the reaction, there might be a little bit of a temperature change that is perceivable. So the temperature probe is going to help us there. And the pressure is, when we actually do the reaction, hopefully going to change. Temperature is being measured on this graph up here. Please note, it's not really changing temperature, so we have a nice straight line. That's cool. Pressure is not really changing. Also cool. We haven't done anything to change the pressure. All right, here we go. Here's how we're going to test that pressure. We're going to open said two-way valve. We're going to inject in some amount of air. Notice how it's all gone. We've closed it. Now look here at our pressure setup. It is nice, 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 nice. Holy cow, it spikes up. And now, well, now it's staying constant. Well, that should make sense. That should be the way it goes, because if we don't have any leaks, all the air that we injected from the syringe should be stuck in our flask. Keep your flask in water. Why didn't you tell me to do that? Keep your flask in the water. So the flask should have all the gas volume in there. And I want to point out that what you might see here at the end of your numbers are some fluctuation. Of course, it's not fluctuating for me right now, but it might fluctuate a little bit out there in that 10,000 spot. That's okay. You might see a little bit of fluctuation. Apparently, I'm really great, and I'm not seeing any fluctuation. This is probably the first time in my entire life of not seeing any fluctuation, of course, when we're making a video. Okay, it's not changed. Oh, it fluctuated. It was so exciting. It's not really changing. This is telling us here that our setup doesn't have a leak. This is good. This means that we can now proceed on to the actual reaction. So we want to, because we don't have any dangerous chemicals here, we're going to release the pressure inside our flask, and I'm going to take off said syringe, put it down over there, and we're going to slowly open the valve away from us so that if there is anything in the valve, it's going to go away from us. And here's a nice little sound. Here we go. Listen. Ah, still good. Okay, so pressure goes back to where it was. That's great. That's fantastic. Our system isn't leaking. Cool. Almost time to get going with the reaction. Something to note. Inside our flask, we put, as the instructions told us to, we put 20 milliliters of water. Right, now it was 20.0 because we used this thing, and if we think about our sig figs and our accuracy and precision stuff from Unit 1, we know that there's one sig fig there, so it's 20.0. We put 20.0 milliliters of water in here. Why am I making a deal out of this? We changed the volume of the gas that can fit in our flask, because now 20 milliliters of that total volume that was in our flask is being taken up by water. So that might affect things going forward, because we've changed the total volume because we put 20 milliliters of water inside. Just hint to the wise. To do this reaction, we need magnesium. Come on over here and I'll show you how we're going to do the magnesium. Great. Okay, so this stuff down here, these little bitty strips, this is magnesium. You might know magnesium from such things as sparklers from the 4th of July. This is one of those metals that burns underwater. They use it in special effects. It's kind of fun. We're not going to burn it underwater though, so that's not as fun. This thing is called an analytical balance. You don't usually use these in General Chemistry 1 for most of our stuff because they're pretty expensive. But they do something really amazing, and that is they measure out the mass of something to the, not the tenths, not the hundredths, not the thousandths, but the 10,000ths. So this allows us to get a very precise measurement of the mass of the magnesium that we're actually going to be using. Note it's got these little doors here on the side. This is kind of fun. The doors on the side here prevent airflow from messing up the balance, because this thing is so sensitive that if I do this, it's causing the balance to record a different mass. And I'm just like blowing air over it, but if I do this and I blow air over it, well, I can't mess up the mass. It's very exciting. This thing is really good at what it does, and thusly it's also very expensive. Who would have figured? It works like every other balance though. Make sure it's taired before you start using it. So right now we've got our value that is not 0, so we're going to tare it. Hey, there we go. And we're going to pick a piece of magnesium here. It's very, very exciting. And we're going to try to touch it as little as we possibly can. We're going to open up one of the doors and gently place the magnesium right in there. We're going to give it a second. And hey, there's the mass of the magnesium that we're going to be using for this reaction. Groovy. So we can open this up now. We can take this out, close the door. We don't want that thing getting mucked up. Remember the part where I said it's expensive? We want it to be really nice, so we're going to close the door. We're going to take our magnesium, we're going to put it right there. In order for this reaction to work, we need hydrochloric acid. Okay, a couple of things about hydrochloric acid. It's an acid. It can burn you. Now, this concentration isn't so high such that it's going to cause major irrevocable damage, but still, if you get it on you, you're going to notice. In the case that you get a chemical on you, as with any other chemical that you use, one, you probably already looked up the material safety sheet for what to do in the case of you getting that chemical on you. In this case, what we need to do is immediately go over, if we get it on our hands, which would be at most the only thing that we get it on, we should immediately walk over to a sink and we should use soap and water, wash those hands profusely, whilst having ourselves or someone else get a hold of the laboratory instructor or a TA to just check in and make sure that things are going okay. Okay, hydrochloric acid that we're using is inside this beaker right here. Our instructions tell us that we're going to be using 20 milliliters of it. We're going to use said syringe to get a nice 20 milliliters of it. So before we do that, we're going to put the magnesium in. So we come over to our setup, pop our thing off. Very exciting. We're going to put that over here to the side. We're going to take our magnesium and we're going to do our best job not to drop it in our beaker of water, but inside our Erlenmeyer flask. And it's floating around in there. It's so exciting. Look how cute it is. Oh, it's just having a nice little vacation. Oh, it's so cute. Okay. Reseal this thing up. Good. Again, we need to make sure that we're not going to have a leak, because if we have a leak, we get to do all this over again. You're going to get to do it over 2 other times. It's going to be exciting, because we need 3 runs, remember? Okay. You just don't want to have to do it 4 times to get those 3 runs. It's exciting. So now we've drawn up some of our HCl, okay, and I'm getting close to 20 milliliters. It's just going to be close. It's our excess reagent, so we don't have to have exactly 20 milliliters going in there. We want it to be close, though, because what we're going to have to do, and I'm just barely pushing this up so that I've got enough fluid there. Okay, I don't know about you, but that looks to me about like 18, or is that 19? Well, you decide. You decide. I think it's really 19. I think it's 19. The reason that we want to know that number is because we're going to need to withdraw that amount of gas here in a second. If that doesn't make a lot of sense, just stick with me. We're going to do this together. We come over to said Lager Pro experiment, and we're going to start collecting. So we hit collect. Oh, we're not going to store the latest run. We're going to erase and continue because the latest run was just that test run. Okay, great. And so now we are collecting data, and you're like, well, what are we collecting? Right now we're collecting a baseline. This is just the pressure inside the flask as it is without the reaction going on. While that is going on, I'm going to make sure that my stopper is in the closed position. I'm going to screw on my syringe. All right, so if we look at our data on the screen, we have a nice little straight line for our temperature. We have a nice little straight line for our pressure. So this is going to be our initial pressure, and this will be our initial temperature. Don't know about you, but I think it's time for this reaction to get going. What do you say? So to do this, we're going to, and I'm going to try to get this all in one shot-ish. We're going to open the needle, open the valve, inject in our 19 milliliters of our acid. We're going to withdraw 19 milliliters of gas. Why do we withdraw the 19 milliliters of gas? Well, because we just injected 19 milliliters of a fluid, so it's going to change the volume, which would end up changing the pressure. From our calculation standpoint, that's not something that we can easily differentiate. So if we inject and immediately withdraw 19 milliliters of volume of gas, it's an even swap. So it'll make our calculations easier. Think Indiana Jones and the Temple of Doom if you're old enough to know that reference. Okay, it's still going on in the background. Fantastic. Here we go. Ready? We're going to open. We're going to inject. Going to withdraw, and I'm going to close. And now, the fun should start. So I'm going to quickly bring out the flask here. And you may or may not be able to see bubble formation starting. So see how it's kind of getting a little hazy there around the magnesium? I'm going to swirl her just a little bit. Oh, yeah, there we go. See those bubbles coming off? That's hydrogen gas. It's so exciting. Oh, now we're getting it going. I need to put this back in the container. And so if we did this right, what we'll start to see is on our graph, with this spike, the spike was when we injected in our hydrochloric acid, right? And then we withdrew some of the gas. And so notice the before and the after are pretty much the exact same pressure. That's what you want. We see our pressure over here slightly going up as the reaction is proceeding here. And just so that the screen's a little bit easier to see, I'm going to move this out of the way some. Zoom in. Let's zoom in. Zoom graph in. Enhance. Let's see if we can do it again. Zoom graph in. Enhance. Hey, look, it's starting to go up a little bit. Isn't that exciting? And so what we'll do now is, because our metal is still dissolving, it is still reacting with the hydrochloric acid. And I know that because I look inside my container and I still see metal there, and I still see gas evolution happening. I can't hit stop until all of the metal has completely reacted and I no longer see bubbles. So we are going to patiently wait for this to now complete. All right, so after that fast forward / fade to black and a good amount of time, our reaction is done. We know our reaction is done because we are no longer seeing bubbles being generated. That's a good thing. We can also take a look-see at our data. So if we look at the data, we see that our temperature has remained pretty constant, which is totally cool and in line with what we expected, because we didn't really think that we were going to be able to generate a large amount of heat that we were going to be able to observe using our equipment that we have here today. However, the thing that did change was our pressure. So it's still in the moment collecting, but you can see our pressure now is significantly different from what it started at. And if we look at our graph, this was our initial, this spike was our, when we injected the hydrochloric acid and we took out some of the volume, and then we see this nice steady climb until it levels out. And that leveling out part is what is going to be considered our final pressure. So we can go over to our software. We can ask our software to stop kindly. It will stop kindly. And there's this cool little feature that's called stat it's called for statistics. It's up here at the very top. It's so exciting. We click it, and what it does for us is it now gives us statistics about our information. So for example, in our box, it tells us what the minimum pressure was and at what point in the graph it was. It tells us our maximum and at what point in the graph it was, and the mean, etc., etc. But what we really need to do is just know what that pressure was. When we drag the little cursor here, we can look here and we can say, here's our mean and median for this initial time period. So those are the data values that you'll need. And then we're going to need to change our cursor so that we're telling the software only to look at the data between the cursor, and we're going to drag it out here to the end. And so now here at this portion here at the end, our data is going to be what you see on the screen. So now we can take those differences in our pressures, and that's going to correspond to the pressure of the hydrogen gas that was generated as part of this reaction. Good news is we get to do this experiment now 2 more times so that we actually can verify that the data wasn't just a one-off. You know, for all the reasons that we've talked about in general chemistry thus far regarding duplication of data and why it's so important. So we're going to present to you the information that you'll need for the trials 2 and 3, and then that should be all the information that you need to finish the laboratory experiment here for this lab. One quick note about cleanup, because as you'll note, we have stuff that needs to clean up. Acid was our excess reagent, so we have excess acid inside our flask. This is where you follow proper laboratory procedures in order to clean up your mess. So you would follow the instructions of your instructor or your laboratory teaching assistant so as where to put the chemicals in the right place. Folks, we hope that you've enjoyed our experience here today. If you have questions about anything that you have heard or seen, please reach out to your instructor, and we hope that you have a great day.